Hi, my name is Tony Chen, and today I wanted to talk to you about information flow from one community to another within a social network. And more specifically, I wanted to find out what are the bottleneck edges that kind of restrict information from one vertex to another. In this case, if I were to increase capacity in an edge, it would increase flow of information through the entire network. Now let's look at the graph behind me. You see that I have vertexes A and D as my start and end, and I'm trying to get the most information possible from A to D and be able to find the bottleneck edges that way. So I'm using something called the Ford-Fulkerson algorithm, and you can think of this flow network as a series of pipes where you're trying to get water, the most water to flow from your source to your sink and along pipes. And the amount of water you can push through a pipe network is actually limited by the smallest pipe. So in this case, if I were to try to push water or network information from A to D, I could find a path from A to B to D. And the most information I could push through is actually 2 on this path. The reason, of course, being that this edge right here is only 2. And if I were to try to push 5 through this path, it would burst this pipe, so to speak. Again, the Ford-Fulkerson algorithm, let's find another path, A to C to D. In this case, the maximum here on this path is 3. 3 flow. Now, are we done here? No, we're actually not done. The reason is we actually have another path from A to B to C to D, right? And how much information can we push down this path? This is actually going to be 2. The reason is we already have 3 here. We can only add 2 more to make it a maximum of 5 through here. So add 2 here and add 2 to this 2, which makes it 4. So we can see from this diagram that the bottleneck edges here are 2 and 5. From B to D and C to D. Now, how do we actually find this algorithmically in a much more complicated graph? The answer is the Ford-Fulkerson algorithm says that if we start from A and we go along each edge that's not been completely filled, and each vertex that we meet along the way will actually be part of our minimum cut group. So let's try that. Let's try to go from A to C. No, we can't do that because this is already filled. But we can go from A to B and B to C through these unfilled edges. And from C, we can't really go anywhere. This has already been filled right here. So now we find that A, B, and C are part of our minimum cut group. And what the algorithm says is that any edge leading out of this group is going to be our bottleneck edge. So we can see that B to D and C to D lead out of this group. So these are our bottleneck edges. So, for this problem, the main challenge that I faced was how to transform from my cap graph of individual users and relationships between individual users to relationships between different communities, right? Where each community represents a strongly connected component of individual users, and each edge, in this case, these are weighted edges, each edge represents all the extra community edges that lead from one community to another. For example, I have an edge from C to D here, and that's got a weight of 5. What this actually means in the cap graph context is that there are 5 vertices here with 5 edges that lead to 5 vertices in here. So that's how I got my capacity. Now that transformative step is actually quite involved. And at first, I had thought that I would simply transform it from cap graph to flow network. The problem with that is that cap graph and flow network, they all had their own algorithms. They had a lot of methods already. And when I started adding to them, they started getting really, really long. And a lot of the transformative steps, they don't really seem to fit very well in either cap graph or flow network. And my solution for this, to keep things very neat, is to introduce a third class called a weighted graph. And the weighted graph is simply an intermediary step that handles all of the transformative actions. And that worked very well for my case. And I was able to find, my bottleneck edges no problem. Now, as I went through my projects and found my answer, I found that there's no good way to actually relate what I have here back to the original data set, which is simply relationships between individual users. How do I know which individual edges make up this weighted edge right here, or this weighted edge right here? So I actually introduced a new class called a weighted edge, which is added by a weighted graph. And what the weighted edge actually does is it keeps track of course, the edge weight, the capacity. Not only that, it keeps track of what individual vertices, or from and to vertices for the edge, make up that weighted edge. So at the end of the day, when I got my bottleneck edges, I could actually use a method from the weighted edge, and for each one, get all the individual edges out of that weighted edge, so I can form a actual output that matches up with the data set that I have. All right, that's been my project. I hope you had as much hearing it, had much fun hearing it as I had doing it. Thank you.